So in this video, let me introduce a little bit of a generalization of what we have just done. So earlier I first used the word structure, and later on became basically a binary operation on the set of solution of these rational solutions. The basic idea is we have this nice factorization of the left-hand side where this main variable part is appearing, and when we raise to higher power, it kind of preserved the structure, preserved this shape exactly, and the other factor have exactly like a symmetric shape appeared. And from there we can recover this integer shape of a solution, not integer, that the one that does not involve imaginary number. So we're back to our original unit circle in here. So see if we can kind of generalize and if we can find different type of example that has this same phenomenon. So basically we're entering the higher degree, and if you just go in and try to imitate that simple two-term cases, just like the Pythagorean triple, rationalized that case, and you will easily find that it's not that the same, it's difficult. So here's actually the opposite way. If you look at the term of a higher degree that enters degree 3 kind of number, so we enter like this, x plus y. So I chose the third root of 2. I think it's just one of the simplest thing you can enter. And z times the third root of 2 squared. And if you play with all the field arithmetic with the third root of 2, this is all you're going to get. You can have this in a denominator. It's more difficult to see how do we kind of rationalize the denominator, but it is possible. So I claim that if you add and subtract and multiply and divide of this shape of a number, you can get back to the shape again. So this time it's not going to be just one thing's multiplied. You have to multiply the symmetric shape, 2 more of them, so that they all become rational numbers. And that trick is called a Galois conjugate. So I'm not going to go through why this one works like this, but if I just write down, you will understand what the trick is. So you keep exactly the same rational numbers, but you replace with a different third root of 2 that is available in the complex plane, which is namely third root of 2 multiplied by third root of a unity. So this zeta is a complex number whose third power is 1, and moreover it's not 1. In that case is captured by this quadratic equation. Complex number that satisfy this quadratic equation has this property, and that's primitive third root of unity. So I draw this complex plane. This is where it's 1, and that's where the zeta is, and that's where the zeta squared, and you go back to that. So that's must be 120 degree. So you can use polar form of complex numbers to write down your imaginary number, real part and imaginary part in exact form, because it's a special angle. So algebraically, this also plays like a number with third root is 2. This is a real number that's the third power is 2, but this is a different number whose third power is exactly 2. You can raise to a third power, you can verify that that's exactly 2. So that's the idea behind this Galois conjugate. You play with all different possibility of this thing. So another thing is that zeta squared, this is also another number whose third power is 2. So you replace this real number with a different possibility, and you do that again with the y instead of that third root of attached to it. You can play with a different third root attached to it, and plus here's a third root of 2 squared. I forgot to put the squared in there, and squared with a zeta in there. Alright, then this number has a square relationship. If you square that, you get exactly the square that. If you square this entire thing, I missed that z in there, so I'm going to put the z back in. Then this is going to be squared. If you square that, it's zeta to the fourth, is zeta to the third times zeta to the first. So it can be replaced with a simple form. So all this thing has exactly what they mean by symmetry here. So it's more complicated. Symmetry doesn't look like symmetric at all, but that's the kind of Galois theoretic symmetry that is involved in here. So if you multiply all that out, so that's going to be a lot of multiplication, and we use this property whenever you see zeta to the third, whenever you see zeta squared, you can reduce it to something simpler, and whenever you see a third root of 2 squared, and you can replace the 2. But it turns out if you multiply this symmetric shape, they all disappear, becomes a lot simpler equation. So here it is. If you multiply out, and if you use all the algebraic relations that's available for zeta in the third root of 2, and you realize everything, there's no third root of 2 appearing again, or zeta appearing, they're all gone, and that's the result of this Galois theory. And this is how you do it explicitly. So what happens from here is very difficult to see if there's any structure in the solution of this 3 variable. So this is no longer 2 variable. We're looking at 3 variable x, y, z, and you can see this is not quite homogeneous polynomial. They're all degree 3 here, but this side is at degree 0. It's not homogeneous. It's really truly 3 variable rational solutions we're looking at. So they're coming from triples of rational numbers and satisfying this cubic equation. Right, like that. And I'd like to show, maybe just explain that if I have x, y, z, and I can create a new solution, and it's a lot harder algebraically to how to generate a new solutions there, but the idea is the same. You look at this factorization. If you raise to any higher power, then you will arrive at exactly the same shape. So for example, if I isolate the first factor, and if you raise to nth power, and you have to use this trinomial expansion theorem to see how the coefficients look like, but you can try with second power or third power to see what happened to this all the things. Basically what happens is that if you multiply x and y and z, they all remain rational. So only thing that you have to watch out is that what happened is we multiply this third root of 2 to itself or to the other things. But the key thing is that whenever you have this one raised to some power, which is basically what you're going to end up at, and you can always reduce it to third root of 2 or third root of 2 squared multiplied by some rational numbers, because third root of 2 raised to third power is 2. Whenever you see that much of a power, you can replace it with the rational numbers. So everything is reduced down to first power of a second power of a third root of 2. So if you collect everything that is a third root of 2, that what's in front of it must be a rational number, and square also have a rational number coefficient. So you can rewrite it into that form always. The point is, again, whenever you have a higher power than 2 on 2, then you can use this relationship to rewrite it. So I'm going to look at the second factor in here and see if we can do the same thing, if we can pull out exactly the same relationship. Alright, we are about to raise this one to the nth power. Maybe that's exactly the same nth power. You can still use this second power and third power to see what I'm about to claim is true. But here I'd like to emphasize the property we used here. Although we used this notation of a third root of 2, we didn't really use the fact that the third root of 2 is a real number. Only property that we use here, if you raise that number to the third power, becomes a 2. So if you look at this number here that appeared non-rational part, then if you raise that number to the third power, then this becomes 2, and zeta, if you raise to the third power, becomes 1. So it has exactly the same property. That's the only property used to rewrite this one into that shape. So the algebra that appearing here is exactly the same. There's no simplification or anything except this property that we're holding here. So I would like to claim that if you haven't done the actual calculation, this is really not a proof, just me just explaining. But if you go through some explicit calculation, you will believe that that's exactly the same coefficient that's appearing there. There's nothing special about this r being with this part in here. If you play with the other factor, if you scroll back, you can see that the other one is what's next to y is this shape in here. So if you do the same thing with the r, the same thing is if you raise that number to the third power, that's again a 2. So just using that property, you will end up at exactly the same coefficients. So what I'm claiming here is that if you raise everything in here, this one and that one and that one, to this, raise the same power, then they go back exactly the same shape with exactly the same coefficients. So here I copy that down again. This is the one factor and this is the symmetric shape of the other factor. So if I raise that to the second power here, everything, and I was claiming this one looks exactly like this, x prime, y prime, third root of 2. So like this, it goes back to this new coefficient to exactly the same shape, and the other two factor go back to exactly the same shape, and especially with exactly the same coefficient that was obtained in the first factor. So that's still 1 here. So what that implies is that if you really expand it out, you go back to the original equation. This is x prime to the third. That's exactly the same thing with a different coefficient. So go ahead and replace that degree 3 equation with a different variable in there. Just a 2 times y prime cubed minus 6x prime y prime z prime, I think, and plus 4 z prime cubed equals 1. So that x prime y prime z prime is another solution to that 3-variable cubic equation. So let me introduce what those x primes are. If you actually expand that out, if you actually square this one in here and collect the third root of 2 and third root of 2 squared and all the rational things, what's that x prime and y prime is going to be. So here, back again, x prime, and it turns out those coefficients are like this. So if you have x, y, z, and you can create a new triplet that's a solution to the original equation, 3-variable in degree 3, which was written in here. So this also has a similar structure, namely the binary operation is defined in here.